Okay, now that we have looked at a couple of different approaches to designing hardware, it's worth sort of diving a little bit deeper into one aspect which is more an engineering cost analysis, which is basically the idea of optimization, and in particular to understand the idea of what's called multi-objective optimization, right. So first things first, what do we mean by optimization? I have a set of constraints and I have some kind of a cost function, and I want to optimize the cost function under those constraints, right. The simplest example that you might think about might be something like this. My cost function is f of x equals x squared, and my constraints might be something like mod x less than or equal to 2. Okay. Now, if I gave you this problem, presumably one way that you could go about solving it would be to actually say, okay, let me just plot this picture, right. It looks like a parabola, right, and if I put the restriction saying plus minus 2 out here, this is the range of valid values for x, right, mod x less than or equal to 2. So I have this range of y values, and by looking through this I can find that this is going to be my optimum, right. In this case, optimum basically means minimum, right. Now if I had asked you, but that's valid only if I tell you to minimize f of x equals x squared, right. If my criterion was to maximize, right, then I would basically have a different solution, right. I would basically say, let's say maximize, also I do have a solution, it is either this one or this one, right. So it's not that you have to choose that it's either maximum or minimum and that's the only thing that can be found. Depending on what you have been asked to do, that is your notion of optimization, right. So here I am using the term optimum as either a maximum or a minimum depending on what it is that you want, right. You have basically been given a cost function, a set of constraints, and under those constraints you need to find the optimum value of that cost function, or rather find the value of x that gives you the optimum value of that cost function. Now very often constraints are expressed as inequalities of some kind, right. It could be something like just x less than 5, or in this case mod x less than or equal to 2, or you might have x1 plus x2 greater than 10, 3x1 plus 5x2 plus x1 into x2 less than 29, right. Now this one, x1 plus x2 greater than 10, is an example of what's called a linear inequality. 3x1 plus 5x2 is so far so good, but plus x1 into x2, this is a nonlinear inequality, right. It's valid, there's no problem with having such an inequality like this, but in a lot of cases it turns out that having this kind of inequality makes it a little harder to solve the problem. Not impossible, but harder. So in a lot of common scenarios we actually end up finding that we have sets of linear inequalities and we want to be able to solve a certain cost optimization under those constraints, right. And our goal is basically to optimize the cost function. So this is the generic definition of optimization, right. Given a cost function and given constraints, if it was something fairly simple like f of x equals x square, yes, we can compute it outright and get the answer. So if we had a simple optimization problem, we know how to use calculus, for example, right. Of course we need not have used the graph based approach, right. Even if I gave you something more complicated like x square minus 2x plus 5, right, as my cost function, and then basically asked you for find the optimum, you would basically know that the first thing to do is to basically take the derivative, find f prime x equal to 0, which basically gives us 2x minus 2 equals 0 or x equals 1, right, as the location of the optimum, right. And by plugging in the value over there, I would find that 1 minus 2 plus 5 equals 4 is the value of the optimum, right. So in this way you can basically say that this is one way by which, given any arbitrary function without even knowing how to plot it or what the shape of the function looks like, I can use calculus and find out where the optimum is going to be and what the optimum value is going to be, right. So this is well studied, well known, we do not really have any problems with it. The issue that we might face is that very often we end up with scenarios where the function is not as well defined as something like this, right. It might be a nonlinear function, it might be something, a discrete function which basically jumps for different values of x, right. And there may be constraints on the x values where we say that maybe the some parameter x1 or x2, one of those is only allowed to take integer values, or it can only take certain kinds of fractional values, right, or something from a discrete set. In all those scenarios, it turns out that our straightforward calculus based approaches do not work well. So we need other kinds of approaches, but there are many techniques that are known for solving such systems. Now that is good provided that I have a single cost function f of x, right, but in practice I very often have something more complicated, right. Especially in the context of something like digital design, I am trying to do multiple things all at the same time. I want to be able to optimize for area, right, so that let us say my resource utilization, I do not want to use too many resources. I want to optimize for speed, either the clock frequency or the latency in the number of clock cycles that I am going to use. It could be the power consumption of my entire system. Let us say that I have got a good area which I am not, it is not concerning, it is not occupying too much space, and it is also operating as fast as I need it to. Now my goal might be, can I reduce the power being consumed by the system? And finally I end up of course having the actual cost of the system itself, right. So maybe we have been designing something using an FPGA, but it turns out that it could actually have been solved using an Arduino or a microcontroller of some kind. Then why wouldn't we choose that, right? It is going to be cheaper, easier to build, easier to design, debug, everything, right. So there are multiple objectives that can play a role in deciding whether or not a particular solution is the right one for your problem. You also have many different choices to make, right. For example, you might have architecture selection. The example where I told you about choosing between an FPGA and a microcontroller is one example of an architecture. Choosing a parallel multiplier versus a sequential multiplier is another example. Pipelining is something that we will talk about later, but essentially what it does is it tries to introduce registers as a mode of actually reducing critical paths in circuits, right. You can do resource sharing. Once again, the example of the multipliers comes in over here, right. We can have either the parallel or sequential multiplier. And you might have the clock frequency, which might just be one of the metrics that you can play, or rather one of the parameters that you can play around with, right. And where this plays a role, for example, is you might be able to choose to lower your clock frequency in order to get better power consumption. So it is not always that your goal is to run at the fastest possible clock. What you want to do is to run at a clock that is fast enough to solve your problem, but does not consume too much power. All of this put together falls under this broad topic called design space exploration. All of these options that I have given over here qualify as certain kinds of design space choices. And what you want to do is to explore those choices and try to come up with something which is the best in some sense. Okay. Now there is a catch, right, and this is where the notion of trade-off comes in, and trade-off is something fundamental in any form of engineering, any form of design. Basically what it ultimately tries to say is you cannot simultaneously optimize. You probably have in some scenario a situation where you are not able to simultaneously optimize two criteria, right. There may be scenarios where you can actually do everything, right. You can get a smaller solution which is also faster and consumes less power, in which case great, go with it, right. So I have given a couple of, or rather 3 different possible examples. These are artificial made up numbers, right. It is just sort of something to illustrate a point that I am using over here. Basically what we have at this point is 3 solutions to a problem. I do not know or care what kind of problem it is, right. I am not really interested in whether it is a digital design even, and I do not care what the units of these numbers are right now, right. All that I can say is I want to minimize each metric, okay. I want the minimum area, the minimum time, the minimum power. Now with that in mind, let's compare solution 1 and solution 2, right. 20 versus 40, solution 1 is better. 30 versus 50, solution 1 is better. 20 versus 30, solution 1 is better. So I can pretty much clearly at this point say solution 2 is unnecessary. There is no scenario I can think of based on the information I have where I would prefer to use solution 2 instead of solution 1, right. It does not matter how much time you put into finding it out and who worked on it or whatever, at the end of the day solution 1 is superior in all senses, right. So it's at that point you probably have to say, okay, yeah, maybe it was a temporary step to get to solution 2, but it's not good enough, we want to go with solution 1. The story is different when we talk about solution 1 and solution 3, right. Now let's consider 20 versus 30, yes, solution 1 is still better. But what about time? 30 versus 10, now I find that solution 3 is better, right. And okay, right now I can also look at power, it turns out that in this case solution 1 is actually better, right. But it does not matter, all that I care about is there was at least one metric on which solution 3 has turned out to be better, right. Now what do I do? First things first, I can no longer just discard solution 3. I can't just straight away say that solution 1 is always better. I need to know a little bit more about my problem. If my goal is to find the fastest possible solution, solution 3 is the right one. It does not matter what solution 1 does, right. If I can say, I want some kind of a mix of speed and area and power, then maybe I can come up with some kind of a weighted average, right, assign some kind of weights, 20% weightage to area, 30% to power and the remaining 50% to time, and then based on that compute a metric and say, okay, yeah, maybe solution 3 is actually better after all, right. But it might be that I don't really know what kind of weights to assign, in which case the only thing that I can say is solution 1 and solution 3 are in some sense equivalent, and I am going to put this equivalent within quotes, right. Why within quotes? Because they are not actually equivalent, they are solving the same problem, but they have different metrics, right. So in what sense are we calling them equivalent? And this is where something called the Pareto principle comes into play, which we will talk about in a moment, right. In order to illustrate the Pareto principle, I am just going to use this sequence of pictures out here, right. This is an artificial example, right. Once again, don't worry about what the numbers are. I have two metrics, right, something on the x-axis, something on the y-axis, and this is a possible solution to my problem, right. And what it says is it has something like, let's say, around 24 units on the x-axis and around, let's say, 8 units on the y-axis, okay. So is it a good solution? Well, we don't know, this is the best that we have right now, right. But somebody else comes along, designs something and says, hey, I can do better, right. Better in what sense? I am able to reduce my x-axis cost by this much. The problem, my y-axis went up by a whole lot, okay. Now if your only goal is to reduce your x-axis as much as possible, then maybe this is worthwhile. So you can't just say that because y-axis went up by a factor of 4, that's immediately rule it out and say, okay, this is rubbish. No, you don't know enough about the problem to say that, right. So right now what I can do is mark both of these, and this red line that's joining them is sort of like a wave front, right. It's sort of saying, okay, this is a set of solutions I have so far, but among those I find that both of these are basically valid. I cannot eliminate any one of them. Now what about this one, right? I come up with a third solution, which incidentally, interestingly, also turns out to be, well, it doesn't really matter whether it was over here or whether it was over here. It turns out that this is actually also a and sort of equivalent or optimal solution in some sense. Why? Because if I consider the three solutions as A, B and C, right, on the x-axis B is better than A, whereas on the y-axis A is better than B, right. Similarly, on the x-axis C is better on the y-axis B is better, right. So if I take any pair of these, A versus B or B versus C or A versus C, I can find at least one of the metrics in which one is better and another metric in which the other is better. So I can't say anything about any one of them being fundamentally, discardable. On the other hand, let's say I do some more analysis and come up with one more solution like this. At this point I can pretty much say, this solution is unlikely, right. I mean, I don't need to consider it for anything, right, because I definitely have at least 3 solutions, or at least I have this one solution out here and this other solution out here that are superior to this one. Now if I had only this solution, right, and I was trying to compare it with this, then these two are equivalent, but both B and A are better than D, right. So I don't need to consider D anymore. I have something which is better than D in every sense. A couple of more examples. This one, let's say E is also beaten by A. It would have been an optimal point if I did not have A and I only had B and C, right. But because I do have A over here, A completely dominates, right, E, right. I can add more of that, and then suddenly I find that one new point came along out here which basically says, hey look, it didn't matter about B and C. This new point, let me call it G, right, is better than C and G is better than B, but A and G are still equivalent because I cannot say that G is better than A in all dimensions. I add one more and eventually I end up with H, and here what I find is A, G and H are equivalent, but nobody else really fits the bill over here, right. Any other solution that I have is completely dominated by at least one, if not more, of these solutions. It doesn't have to be dominated by all of the other solutions, at least one of the solutions. So for example, this one out here, right, I'll just call it X, right. A completely dominates X, and as far as this is concerned, if I call this Y, G completely dominates Y. What about A versus Y? No, A does not dominate Y. Similarly, G does not dominate X, but I don't care. There's at least one solution that dominates X, one solution that dominates Y. They are no longer in the picture. But A, G and H in this case are equivalent. The specific term that is used for this is called Pareto optimality, right? This term Pareto, it's the name of a person, an economist who actually did a lot of work on understanding the trade-offs in various kinds of economic principles, and this is sort of where the idea comes from. It can sort of be summarized as saying that you cannot improve one without sacrificing another. Pareto dominance basically means that A is better than B on all metrics. Pareto equivalence says that A is better than C on one metric, C is better than A on at least one other metric, right? And this is the sense in which we talk about Pareto dominance and Pareto equivalence. And ultimately, when we are trying to do digital designs, what we want is to come up with a set of Pareto optimal solutions from which we can finally choose and say that, look, this is a good solution, or these can be discarded because they are completely overruled by some other solution that I have come up with.